All right, so today we're joined by Neil. Neil works at AWS, and we're going to be doing a small mock interview today. Thanks for doing this, Neil.
Yeah, thanks for having me. I'm Neil, and I work at AWS, and I work on AWS Snowball, which is a device that you can order from AWS, and they'll ship it to your location. And it lets you do similar workloads that you'd be able to do in the cloud, like S3 and EC2 instances. If you have bad internet or you want to collect data in some remote location, it's like a good option for you.
Right. Is this something where you have the device and then you can perform operations and they're synced later with the cloud?
There's a little bit where you can sync later with the cloud. So one of the things we do is data import and export.
Okay.
So say you have a ton of data in your server, even petabyte, you're not gonna be able to send it over the internet fast enough.
Right.
So you can order a Snowball and load all your data up, send it back to AWS, and then we'll put it in S3 for you.
You'll have the physical device and you can actually just send it back to the AWS team.
Yeah.
Oh, interesting.
And then they'll ingest that data to the cloud for you.
Interesting.
And it goes the other way too. If you have a lot of data in the cloud and you want it on-prem, to your own company, you can order a device, we'll load your data on and then send it to you.
So we're going to be doing a single question, a data structure algorithm question. If you're ready, we can hop straight into the problem.
Yeah, sure. Let's do it.
So in the problem we're dealing with, we're going to get a single input array, and it's going to be called jumps. And essentially, each of these indices are going to represent something. Our goal essentially is let's imagine we have a character. A character is going to start at index 0. And each of these indices represents a maximum amount of jumps we can take forward from a given indice I, right? And so we start at index 0, and we're trying to get to the last index, the length -1 index. And so each of these indices tells us how many jumps we can go forward at maximum from a position. So if we look at index 0 in this jumps array, we can go 4 jumps forward, right? So if we're sitting at index 0, I can hop to index 1, I can hop to index 2, I can hop to index 3, and I can hop to index 4. So you can see how it's index 0 plus 4. 4 is the value at index 0, and it lets us hop all the way to this indice, which is 0, 1, 2, 3, 4, right? And so that's one jump. And then once we're sitting at this indice, we can get all the way to the end because we can do 6 jumps from this indice.
Mm-hmm.
And so the goal is we want to return the minimum amount of hops that it would take to go from index 0 to the final index, given the constraints we have at any one of these indices in terms of maximum hops forward we can go. And so when we're starting from this index 0, we can hop to any one of these indices that we're allowed to hop to. And we may be advantaged to hop to different ones, but essentially that is the constraint that every index gives us. And the overarching goal is get from the start, index 0, to the final index with the minimum hops. So singular input jumps array, the output would be 2 in this case. We could have done the hop from index 0 to index 0, 1, 2, 3, 4, and then we could hop all the way to the end because this 6 gives us free reign over the rest of the array. And so this is just one input example. You can ask me questions about any other clarifications, any other edge cases, and there's another example here. But that's the overarching goal. And if you have any clarifications, you can ask me, and so on.
Cool.
If you're enjoying this video, we have plenty more awesome data structure algorithm and system design explanations on interviewpen.com. You can ask us any questions you have about any kind of topics surrounding data structures and algorithms and system design. We release 2 to 4 videos a week. You can run your code. You can talk to a personalized AI teaching assistant. And yeah, the site's pretty great. Anyway, enjoy the video.
Yeah, this is an interesting problem. So you're trying to get to the last index.
Yes, that's correct.
Okay. Interesting. So we have a list of... It's basically a list of number of hops you can take. From any given index. Cool. So I guess there would be no reason to wrap around the end because you would just be there at that point.
Yeah, that's a great question. So we're only concerned on going from index 0 all the way to the end. I would imagine we could have a variant where, maybe there's wraparound and there's some, way we could define that, but we're only interested in going from the first index, index 0 all the way to the end. And that's a good question in the case of this 6. The 6 unlocks every other indice all the way to the end. If there are other indices, it would unlock them, but, it kind of runs over the array. So we're only interested in that scoped kind of, yeah.
Got it. And we return the minimum number of hops?
Yes.
Okay.
So
minimum number of indices that you stop at and then use that value.
Yes.
Right? Yeah.
Yes.
Okay.
So let's imagine these are stones and we're trying to hop across a pond. And at each of the stones, there's a number you need to read to say how many stones forward you can jump. Yeah. We're going to count if we do one hop, jumping from one stone to another, that costs one hop.
Right.
And essentially we're trying to go from the start to the end. So that is that is the cost we're trying to minimize for, minimal hops to make it to the end. Yeah.
I see. Yeah. So it's almost like minimal stops because you have to stop at an index and then take that value, and you can go that amount forward, but you also can't, and you could also go less. Like, so like if we're at zero, if we're at index 0, we can go 4 hops, but we might want to stop early. And I guess you'd want to stop early if the thing that gets you a low number of hops is stopping on a high number.
Right.
So like here we want to stop at 6. Okay, cool.
And so that's a great point you bring up. It may advantage us to stop short if there's a high number. That's a good insight. Yeah.
Cool. Okay, let's see what's going on. Okay, we got some test cases. Just trying to see like what's going on here. Okay, so this is min jumps, and then these are the tests we're gonna run.
Yeah, and hopefully all these test cases are correct. In this case, we would have this is the same case we looked at. We would imagine the min jumps are 2. This is another test case. And these test cases are all tests you can run.
Interesting. And there can't be any negatives, I'm assuming.
So these are all going to be non-negative integers. We could have 0 potentially, and that would be a show-stopping thing.
Right.
But yes, it's all going to be non-negative integers.
Yeah, 0 is an interesting case because if you land at 0, you're stuck.
Right.
So 0.
Right.
0 is there, but we don't want to land on it.
Yeah.
Let's just call this like 0 case. We don't want to land there. We can't land there. Okay. Yeah. So I guess first, like what I'll do is just think about the brute force, or just the A solution that I think will work. Mm-hmm. So, so for like trying all solutions, right. We could just start here, and you could just take the full amount. You could just take the full amount every time, which is interesting. It's not going to help you get to a result, but
right.
So let's think about like what the different combos are. I mean, the output, we just want to know what the minimum number of hops is. So let's just think about trying everything.
So what are you kind of initially thinking right now? Like what?
Yeah. So I mean, obviously I have to process this array in some way.
Right.
I think for a better solution, I could maybe like build a tree or something because we have all the info here. Like we have the pond, like as you say, but
right.
This is not a great way. This is not a great form of the data that's going to allow me to figure out the like minimum number of hops easily.
Right. I see what you're saying. So you're thinking about, okay, we see this constraint set, and it actually creates like a sort of, let's imagine these are rocks we can hop between. There's like a graph of sorts, like where there's edges we can hop between. And that doesn't really tell us the best answer. That just gives us a representation of the problem data wise. And so, we would need to find like what is the best path.
Yeah, like I think it's good with a pond example, right? Like you have a pond and you have these basically different paths, but like this data right here in the array, it's not laid out in a way where I'm like, when I'm trying to find the solution, it doesn't look like a pond. Basically, like it's not going to help me very much this way. Yeah, so that's why I would think about tree. Or like graph, right? So I was going to do brute force, but I'm just going to see if I can think of a decent way to like represent this.
Right.
So 2-1 gives you 1 as the minimum hop.
Yeah.
But if I wanted to put this in a different format, like a graph.
Yeah. What would the nodes be? What would the edges be?
Yeah, right. So the nodes will be...
And we don't have to go down this path. We're thinking about how we represent the problem. This may not necessarily like lead us to like an implementable solution. It may be too complex to implement, but from a theoretical lens, this is like a way to think about it. I don't know if we should follow this as like a way we could bring this to code, but anyway, we can take this whatever path you'd like. Yeah,
and that's the thing. Like I would explore the solution and see if I think it will be beneficial. But yeah, so like if I were to to represent it as a graph. The node would be each indice, because each indice is a distance from the end.
Right.
Yeah.
Yeah, I would agree. We would imagine the nodes are the indices, and then at every index we have that integer, and then that gives us some information.
Right. So one thing is you could have the node be an index and also carry the information of the number of, what is it called? Number of hops? Yeah, number of hops.
Number of hops you can go.
And then thinking about this in terms of a graph, right?
Right.
So we have nodes would be each index. And in the pond example, it's like the rock that you're at. And the node can carry the info of number of hops that you are able to take.
Yes. And also to guide our thinking, we have nodes, we have edges, which are, the relationship between these rocks. What can we do if we can think of this as a graph? Like, what does that unlock for us in terms of?
Yeah, definitely. So the advantage of putting this into a graph is that if we have it in a graph that's well represented, we can do efficient operations on that graph. And I also think that if we get this into a good graph format, we might be able to very easily pull out this minimum number of hops. Is that what it is?
Yes.
Minimum number of hops.
Yeah.
But yeah, I'll just keep going down this rabbit hole. So
and how would we do that? Like, let's imagine we had this represented. It doesn't necessarily mean we need to create an in-memory graph. It's just if we're thinking about this graph, we're able to search it. How do we find a shortest path between two nodes in a graph, right? We have this start node, this end node. How do we find the shortest path given the constraints, drawing these edges and so on? We don't have to think of this as a graph. There's a plainer way we could just straight up just do this. But modeling the problem this way is also valid.
Yeah, that's a good point. We shouldn't build a graph if we don't have to. And that's a very good point. Yeah, and I think this representation is probably pretty good. And you can represent a tree in an array if it's sorted properly. But looking at this,
right,
we are starting at the beginning and ending at the end. So we might be able to just walk through this array from the beginning to the end and try and determine the number of hops along the way,
right,
the minimum number of hops along the way.
Right.
Or do something like walk through the array and record the different options.
Yes. I think that's an interesting path. Yeah. What do you think is the best we could do here? I guess that's another place. You don't necessarily have to answer, but that's a place my mind wonders. What is the best we can do here? And I mean, you kind of just said it. It's the best I imagine maybe linear. I don't know if an algorithm exists for that, but we have a linear structure here, and we're going to have to look at all of the elements. So the best,
exactly.
We can't do something logarithmic here unless we know some special property. So that's just an aside, but I like the path we're on in terms of, searching the graph and so on. We want to find the shortest path. So the way you're modeling the problem, I like. I feel like we need to be more methodical about how do we find the smallest path. We could model it as a graph. That's one way to do it. And you talked about exhaustively checking from a certain position, how many hops could we take from the end? Would there be a way we could exhaustively do a checking like that? And it is valid to come up with a brute force solution to this problem. Would we be able to do something like that?
Yeah. So you're jogging my memory, and
right.
So one thing we should think about is if we can possibly break this into subproblems.
Beautiful. That's an interesting.
And you're jogging my
path you're on there.
You're jogging. So first of all, I'm killing the graph idea because
I think the graph idea is a completely concrete straightforward.
It's a way.
Yeah. Yes. Is completely valid.
And you should. Yeah. I think when you're doing a problem, you should think about different popular ways,
right,
or not popular, but useful ways to
right,
to do it. But one of them,
essentially, we would be treating it as a graph if we were to subproblem things down and find an optimal substructure or whatever. But anyway, yeah, you can continue. I think you're on a good path with that.
The part that kind of jogged my memory is you were saying, how would we, even if we check everything, how do we know that this is the best path?
Right. And so then the question becomes, if you're sitting at that index 0, what does the subproblem become? What does the checking look like?
We should think about two things.
Right.
One, can we break it into subproblems? And then the other thing is, how do we know what the right solution is? So let's do number 2.
Mm-hmm.
How do we know what the right solution is? So even if we have all the total paths, how do we know the best? So for every path, independent path through this array, the path will have a number of hops, and it will also have the specific path. So like this one, if we come up with the solution of 3, that would be the output, but we might also we might want to know that path. So
Right.
that would be like, how do I traverse? So I start at 0. That one's a given because you always start at 0.
Right.
Then we just go to index 1, 2, 3, and then we're done. So if we say a path is a list of indices.
And we don't have to necessarily track paths. Like at the end of the day, we just want the output.
Right. And that's one thing about this problem that is kind of a hint. All you have to give is the output. You don't have to necessarily know how you got there, because some problems will have you give the actual path, or the path and the output.
So I think we should like shift our thinking to, what if we're sitting at index 0, what would it look like to search for an optimal path? Would we trial paths? Is there like an optimal strategy?
Yeah, so I think that like one thing is I think you can do this problem in like O of n time.
Okay.
So I should just be able to walk through this array and basically take a greedy approach.
Right.
And what I mean by that is like,
right.
As I choose my destinations or my where I'm going to stop, where I'm going to hop to,
right.
I'll always choose whichever destination will get me the furthest in the array.
Right.
And that should result in the best path.
Right. And so like, what would that look like? Like say we're sitting at index 0. Like what do you mean specifically?
Yeah. So when we're at index 0, basically our choices in this example at the top, our choices are 1 hop, 2 hop, 3 hop, or 4 hop.
Right. And so it's this set of possibilities. Okay.
Exactly.
So those are the possible jumps we could go to.
Exactly.
Right.
So out of these choices in front of me, I want to pick whichever one would lend me the ability to go the furthest.
Right.
With that choice.
Okay.
So here, and we also have to consider that these are in an order. So like, say we have like a 3 and a 3,
right.
We always want to choose the one that gets us furthest.
Right.
So if we're considering 3 as a choice, choosing to stop at 3 will allow me to then take 3 further hops forward, max.
Right.
So that would be
this basically.
1, 2, 3 to here.
Yeah. The 4, 2, 6. Yeah. Okay.
And what I would do is I'll look at all my options.
Okay.
And compute what the end like distance is that I make by stopping there and choosing that number.
Right.
So here for 3 would allow me to reach to index 4. If I choose 4, I'll be able to get further. 1, 2, 3, 4.
Yeah.
Like this is index 6. For 2 as the choice, I'll be able to hop, bam, bam. That will get me to 1. This element.
Right.
And then 6. Looking at that as the current choice, that will get me bam, 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 bam,
1,
bam
2.
to here.
So I see what you're saying. So essentially you're saying, okay, here are the possible values we could jump to for jump 0. And you're saying like, which one pushes the frontier of where we can reach the best? And this is greedy. Obviously, like initially when you bring up a greedy approach, I'm like, does this always work? What cases could this break? And I guess we could talk about that. But essentially what you're saying is these are the jumps we could possibly do. Which one pushes this frontier as far as possible? And that is the one that advantages us the most because we already can reach any one of these positions with jump 0. With the next jump, which one lets us reach the farthest? And so, that is the most expansive jump to do.
Right.
And it's greedy in terms of we don't know where this takes us later. But
right.
So I think this approach is interesting. Like how can this break? Like, is this always correct? Is like the thing I would think next.
Yeah. So let's think of some ways that we might be able to break this. in addition to like what could break it,
Right.
I also like to think about like why is it right? And the reason why I think greedy would work here is because you have to make a decision and you can't go back, basically. Like when you choose the next place to hop to, the rest of the array is just irrelevant. Like what's behind you is irrelevant.
Right.
We're only looking forward. So out of these choices, once we hop to one of these,
Right.
our next choices are already defined.
Yeah.
So like for this, once we hop here and decide that we're going to hop there, this is going to be our next choices.
Yeah.
And once we hop here, these are going to be our next choices.
Right. And so we
Once
only
hop
need
here.
that single look ahead to expand us out as far
Right.
as possible.
You're basically going to you're going to peek ahead
Peek ahead and take.
at where your choices will take you in the next hop.
Right.
And out of those 4 choices, you'll know the best choice because you'll know the implications of that choice. And what we're concerned about is how to get to the end
Right.
the fastest.
Yeah. And here's an interjection. This is something I think about when I think about greedy algorithms. It's like, 1, like how can we break this? 2, are we looking at all possibilities at the decision junction that we might overlook that may make us miss an optimal answer later? To me, it seems like this would probably look at all of the optimal kind of jumps we could have reached because they would have pushed the frontier out as far as possible anyway. So those are 2 things I'm thinking. But anyway, we seem like this is, to me, this seems like a good path. I think we can move to implementing this if you're comfortable with that. I believe this would be correct.
Let's try out the greedy approach. So I'll just start by putting this in a while loop. And let's also declare the current index. Current. So we're starting at 0. So while current is less than length of jumps -1. So basically what this means is we'll stop at the end. Let's also keep track of the number of hops that we've had to take. So starting at 0 hops. And then after this, when the while loop is about to go around again, we'll just hops plus equal 1. Does that work in Python? Okay. Current will set based on where we want to go. Okay, so what I'm going to do is first pull out the choices. That's what in this example,
Right.
It's going to be this subarray.
And then from those choices, we'd extract like a frontier.
Right. Like from those choices, we will basically filter through those choices and find out which one is going to get us the furthest. And we're not going to necessarily stop at the furthest, but what I mean by get us the furthest is get us the biggest next set of choices. The next set of choices that reaches the furthest out.
Right.
So choices is going to be a subarray of jumps.
And I don't think we necessarily need to take a subarray. We could just iterate over those indices and then, kind of do an offset, but we could extract a subarray as well.
Yeah, that's a good point. We could totally just use the current index. So basically, choices is going to be current index plus 1. This is going to be inclusive. Current plus 1. And then up until current plus jumps at current. Cool. So let's iterate over that range. So let's do for I in range. So I'm going to just get I think I can get a range like this. For I in range. And range is exclusive.
Yeah. I think it's inclusive left bound and then exclusive.
Exclusive,
right. That's
right.
what you see in like every language. And then remember, we want to add currents to the jumps. I think add currents to the jumps at current. If that makes sense.
Add current to the jumps at current. Yeah.
Because we're offsetting.
Because we're not always starting at 0. So now we get the proper range.
Isn't it exclusive on the end?
Yeah,
that's
it's
correct.
exclusive
Yeah,
on the end,
yeah,
so we have to add an extra. So I guess this is now a soft brace. Yeah.
So now we can iterate over, the places
choices
we could go. And then we need to, do this intermediate kind of frontier checking.
Right. So basically, I'm also going to keep some other. Okay, we have current. So at each I, let's pull out I won't call it like span yet, but I'll just say distance is jumps at I. So let's just do end index is going to be current index plus distance plus I plus 1. right? Because the reason I say +1 is because
I don't think we need to do the +1. The +1 was we wanted to do the exclusive on that right bound, but I mean, maybe we do need the +1. I have a feeling we don't. Not totally sure.
So end index, I want to be the index that the max index that we can choose after choosing that choice.
Let's imagine we take index 0. We can hop 4, 1, 2, 3, 4. So that's index 0 plus 4. And that brings us to index 4. And so the farthest place we could have hopped is index 4. And that's what we want. So that's why I say we wouldn't want the +1. But yeah, just you should double check that logic.
Yeah. So let me just go through that. So current in this case starts at 0. So end index and I is going to be 1,
right,
for the first iteration. In order to compute the end index of that range, of that span, it's going to be current plus the distance. So that's going to be 0, 1, 2, 3.
It seems right to me. I think the current plus distance seems right.
We're here and we're checking this. So we should get 0, 1, 2, 3, 4. Yeah. So it is +1.
So
4.
yeah, if our basis is index 1, we can hop 1, 2, 3 up to index 4, 0, 1, 2, 3, 4.
4.
But that would be index 1 plus 3, right? So it would be current is index 1.
Oh, so instead of, right. So it's plus saying. I.
Yeah, exactly. I plus the distance. Yes. Distance plus I is the farthest we can jump. Current itself is overarchingly the previous jump.
Right.
Yeah, I see what you're saying.
But
we were on the same page, yeah.
So it is just distance plus I.
Yes,
yeah.
Correct.
Because we're already relating that to the range up here. Yeah, so basically what I want to do is look at all the choices and figure out which one has the highest end index. All the choices in front of me.
Right.
I'll just do max. I'll just keep a counter of like max and index, and we'll just initialize it to -1 because that's always going to be lower. And then, or this is going to be max, end index. And then we also need the index of the choice because we want to not only know where we're going to end up, but we want to know which choice will give us that end, so we can actually make that choice once we figure it out.
And then change the current.
So, Python, we don't need this. If end index is greater than max end index, and we'll set max end index. X is going to be end index. And then we're going to set max end index choice to be I.
Yeah. It was well formatted, yeah. And then I imagine at the end of this iteration, we'll have what we want. And then we can actually do the state transition.
Right. So at the end of this, we'll know the next choice to make. So this is going to find the, let's just call it best next stop. And I think with what we have here, we can at least find the next best hop. And I just realized this is also jumps I. Okay, cool. So we're going to iterate over the span of choices, and we're going to pick what we think is the best choice. So now I think I just need to reset some of these variables outside the for loop. So let me get the spacing right. So current is going to then be max and index choice. And yeah, from here, I think we're pretty good for these temp variables. These will get reset at the top of the while for each new choice. We're also keeping count of how many hops we've done already, which is what we need to know at the end. I don't think we need this print anymore. Yeah, other than that, I think all we need to do is let the while loop end and return hops. What's up with this spacing? There we go. I think we're doing fine here. I think at this point, I'll just try running it and see if we can get any of these test cases.
Yeah, we can run it and figure things out. Maybe we could just do one test case. All right, so I think we can pause with the debugging. I think we're at a solid point. I think the conceptual basis for what we're trying to do is down, and I think we're basically there in terms of what we're trying to do. So let's kind of hop to kind of thinking about how do we analyze this? What would the time be? And how would you analyze the space usage as well?
Yeah, definitely. So as far as space, we're not doing anything crazy. So if we think about the memory that this is using, we have some variables. They're just integers, and that's going to be fairly small, and more importantly, it's going to be constant.
Right.
So we're just keeping these integers. It's not like we're creating integers for every index,
right,
or something like that.
Yeah.
These are just a constant amount. So for the space, it's just like n times the number of ints that we have.
Well, is it n times the number of ints? I mean, you were pretty correct in just saying it's constant. To me, it looks like there's nothing.
Yeah, this is just so this is just a pointer.
Right.
This is an int. So I mean, the pointer is also like a int size or close to an int size. And that's just for every variable that we create. And then range is something here to be considered. Like this is I'm not sure of like the exact implementation, but we are probably creating something here.
Some underlying
an object that produces a sequence of integers. So it's like an iterator. This is probably not producing like anything to be concerned about. So It's going to be like basically like O of 1 space is what I would say.
Yeah. I would agree. It seems like it's constant. And then
that's space. And then for time, so we have a while loop. So this while loop is going to be like at max n, because there's only n possible hops or m around n. Yeah. Mm-hmm. So for the while loop, I would say n, and then that's n times the possible length of the subarray. Right.
And this is interesting.
Yeah.
I know.
And then
we did it again.
And then now you're thinking how
it seems that this would be n squared. You look at it and
it could be.
There's a linear bound outside. There's seemingly fractional work of the linear amount inside. But to me, I'm thinking, what is actually happening here?
Yeah.
And what's actually happening is that we're considering a range from a certain position, and then we're hopping over that whole range, and we're not reconsidering that range again. So it seems that there's no dependent work.
Right.
That's like what I suspect, right?
Yeah, and also like another thing to consider is...
But I don't know. I could be completely wrong, but to me that seems like it's overarchingly linear.
Yeah, and also like the size of this loop right here,
right?
It's never going to be greater than n.
Right.
And also at the same time, current is always... it's always incremented.
Right. So we're never going back on ourselves. We're always going to take the maximal choice that takes us beyond like the maximal span of where the next jump could go. And, we don't reconsider pieces of the n that we just skipped over. So it seems linear. I might be wrong, but, we could loose bound it and say, okay, maybe it's quadratic, but I have a feeling it is linear.
You mean like an upper bound?
Yeah, the upper bound could be a loose upper bound at n squared, and that would be technically correct.
Yeah, we know that an upper bound would be n squared, but I think we could probably... Do you think we can prove that it's less than n squared?
I think we can. To me, it seems like it's probably linear. Yeah.
Maybe we should ask ChatGPT. How do we prove that this is not an n squared solution?
Okay, so in terms of time, I think we're good on time and space. So let's kind of take a step back and kind of discuss the meta of kind of how things went, and like how did you think that went, and maybe how does that compare to like your other interview experiences and so on.
Yeah, so for this one, I definitely say that like it took me like a little longer compared to some of my other interviews, and that's mainly just because like I'm not really practicing anymore.
Right. I mean, this is I pulled up today and I'm like, okay, let's do this.
Yeah.
There's no real pre-prep.
But
I've never seen this problem.
Yeah, so. That's fine. So as far as like how I did, I think I did okay. I think if I were really trying to like laser in and do my absolute best, I would just look at the problem and kind of go for what I always like to do is look at the problem, think about a way to solve it, and just start writing that way. And as I'm writing that way, I might figure out like, hey, there's a better way to do this, or we're checking different solutions multiple times. We shouldn't have to.
Right.
And then I can write a better version. But I like to get something down, a version down that works. And then if you have extra time, you can kind of consider the time complexity and then try and improve it. But like for me, when I go into an interview and like I'm trying to do my best, first I want to get a working solution. I think that's important. Like you want to demonstrate that you know how to program and you can lean on the language. And then second, if I can do that, get a working solution, I'll try and improve that solution down. And I don't think interviewers will like dock you because you ran out of time. I think if you can take your time and like write a solution and analyze it and think about better solutions, then you're going to do great. Yeah.
Right.
Like I've been in interviews where I wrote a suboptimal solution and then we were close to running out of time and the interviewer just kind of said, hey, like, can you think of any other more optimal solutions? And as long as you can, kind of like explore different ways to do it with the interviewer and show that you have a good grasp of like the language, but also the time complexity, I think you're gonna do fine, even if you don't get the best solution. Yeah, and like compared to my other interview questions, I would say it's about the same. Like difficulty wise, sometimes you'll get more like free text, like a lot of free text.
Right.
But being able to boil it down and just get something simple like this is also good. But yeah, as far as difficulty, I would say it's like about the same. Usually I've gotten problems where there's multiple, usually like more than 2 complexity ways to solve it. And ideally you can at least get the one in the middle, that one that's like in the middle as best. So I'd say it's like about the same.
And so that's the interview. I want to thank Neil for his time. And if you want to go practice this full problem, you can practice it on interviewpen.com. You can practice a ton of other questions like this. We publish 2 to 4 videos a week on data structures and algorithms and system design. And that's all. Thanks for watching.
And yeah, thanks for having me.